Welcome to my presentation on a biochemical technique. I will be presenting on the details of differential scanning fluorimetry, DSF, and how it can be used in science. Differential scanning fluorimetry was first described in 1991 in a method that looks very different from what DSF looks like today. It was conducted using 1,8 ANS and quartz cuvettes similar to the ones we ran in the kinetics lab. In 2004, the method was refined and adapted to be conducted in a qPCR instrument with a fluorescent dye called Cipro Orange. This is still the most commonly used dye. DSF is now a rapid and affordable biophysical biochemical technique that has many applications ranging from protein folding state detection to ligand identification. This technique is commonly used in early drug discovery. 1,8 ANS, as seen in the structure to the right, was the original dye used in DSF. In water, the compound remains colorless, but when it binds to a membrane, it becomes noticeably fluorescent like the picture to the left. This behavior made it a sensitive indicator of protein folding and conformational changes. Prior to modern-day PCR machines, DSF had to be conducted one cuvette at a time due to the lack of a plate reader, making it a very time-consuming and laborious method. Since 2004, Cipro Orange has been the most commonly used fluorescent dye in DSF. It has an excitation wavelength that is compatible with qPCR instruments, which is very commonly found in research labs. Cipro Orange binds non-specifically to hydrophobic surfaces, and similar to ANS, water eliminates its fluorescence. So now that we know a little bit about the history behind DSF and how it has been adjusted into what we now know to be DSF, let's talk about how it works. DSF is considered to be a type of thermal shift assay, and a thermal shift assay is run to measure the changes in thermal denaturation temperature, which basically means that it looks at how a protein unfolds at different temperatures. DSF works by adding a fluorescent dye to the protein that binds to the hydrophobic core. Once the protein unfolds, the fluorescence is exposed and read by the PCR instrument. In this picture, we see the folded protein in green and then the Cipro dye in the orange stars. As the protein begins to unfold, the orange stars of the dye begin to bind to those hydrophobic inner core of that protein, and it unfolds, exposing the total fluorescence of the protein. As the Cipro is binding and the protein is unfolding in the PCR instrument is gathering data that looks like this. On the y-axis, we have the fluorescence, which is often measured in fluorescence units, and on the x-axis, we have temperature. As the temperature inside the PCR increases, the fluorescence is red and indicated by the peak on the graph. The greater the unfolding, the greater the fluorescence. This peak gives us the TM, which stands for melting temperature, and the fluorescence peak. The PCR instrument that we have at school pictured here is made by a company called CHAI. More specifically, we have a qPCR, which stands for real-time or quantitative PCR. It is located in Dr. Drace's lab, and he probably paid between $5,000 and $7,000 for it, which might not sound very affordable to a college student, but comparatively speaking, it is on the lower end of the cost spectrum compared to other techniques and other more costly PCR machines. These PCR machines can cost up to $140,000, and they have all of the bells and whistles, but a qPCR is what is needed to run a DSF. qPCRs are less expensive and require significantly less labor than other methods, which could produce similar results to a DSF. Other methods to study protein unfolding are biochemical assays, circular dichroism, and differential scanning calorimetry. Biochemical assays, like the name implies, uses different chemical compounds to chemically denature the protein. This is a low-cost option, but they require very specific assay and need catalytic activity of the protein. Both circular dichroism and differential scanning calorimetry both require a large amount of pure protein to work with, and they are low throughput options. One thing to consider when you're conducting a DSF is which type of dye to use, and that totally depends on your protein, whether you choose an intrinsic or an extrinsic dye. An example of an extrinsic dye would be the Cipro Orange, which we talked about, but it must be in an aqueous solution because it does fluoresce when it is exposed to hydrophobic substance. So if you have a protein that has hydrophobic patches around the outside, it wouldn't be an appropriate choice because it would falsely indicate unfolding. An intrinsic dye example is called a GFP, which stands for green fluorescent protein tag. And that tag is fused to your protein of interest, and the signal from this tag is recorded as its location changes based on the proximal location of it within the protein as it's unfolding. Unfortunately, this is a very sensitive approach, and the signal may not successfully be able to identify your protein due to the high sensitivity. The general methodology of DSF would require you to get all of your materials together. You would need a qPCR instrument, your protein of interest, the compound that you're testing with your protein, the appropriate fluorescent dye, and an aqueous buffer such as PBS. You would then combine your protein, compound being studied, dye, and the buffer into PCR wells, and then you would centrifuge those wells together to thoroughly mix all of your materials and remove any bubbles. And then you would place those wells into the PCR, adjust your heat range, because remember we are denaturing with heat, and then you would let the PCR run, and then afterwards you would analyze that data and compare your different melting temperatures between the different concentrations of that compound of interest in relation to how it made your protein react. Once you've done all that, you can overlay the fluorescence peaks from the different concentrations and see the impact that the compound had on the thermal denaturation of the protein. The results might look like one of the examples listed, where the peaks have moved or changed shape altogether. I really liked examples B and D, where you can clearly see the shift in Tm. The compound in these examples had to have stabilized the protein so that it didn't unfold until a greater temperature was reached. So in summary, DSF stands for differential scanning fluorimetry, and it is a type of thermal shift assay, meaning that it uses heat to denature the protein. The instrument used to perform this technique is a qPCR, and the way that it works is by using a fluorescent dye that binds to the hydrophobic core of the protein as it unfolds. The fluorescent peaks and the melting temperatures gathered from each concentration can be compared to see the effect that the compound of interest had on the protein. Thank you guys for watching my video. I apologize for all of my stutters, and also I apologize for the watermark. It was a free trial and it's $300 to remove it, so it stayed. Anyways, I hope you learned something, and I look forward to watching all of your videos.